In the quantum universe, information takes on a new form, not as the ordinary 0s and 1s, but as quantum bits or qubits. Now, you might be wondering, what on earth are qubits? Well, if bits are the building blocks of classical computing, qubits are the building blocks of quantum computing, but they're far from ordinary. Unlike bits, which can be either 0 or 1, qubits can be both 0 and 1 at the same time. This is due to a quantum phenomenon known as superposition. Here's a way to picture it. Imagine a globe. A classical bit could be at either the north or south pole, but a qubit? It could be any point on the globe, representing a state of superposition. This ability to exist in multiple states simultaneously gives quantum computing its immense potential. This is the quantum world where qubits exist in multiple states simultaneously thanks to superposition. Now let's step into the realm of entanglement, where the magic really happens. Picture a pair of qubits, quantum twins if you will, linked in a way that would make even the most powerful supercomputers blush. These qubits, no matter how far apart they may be, are entangled. This means that the state of one qubit will instantly affect the state of the other, whether it's in the next room or on the other side of the universe. It's like they're whispering secrets to each other through a quantum hotline that connects them. This isn't just some theoretical curiosity, it's a fundamental principle of quantum mechanics. And it's this principle that could revolutionize the way we communicate, creating channels so secure they're protected by the very laws of physics themselves. This mysterious connection between qubits, known as entanglement, is the cornerstone of quantum communication. In the hands of quantum information theory, ordinary algorithms evolve into quantum algorithms. These are not just your run-of-the-mill procedures. They are powerhouses that leverage the unique properties of quantum mechanics, allowing them to solve complex problems exponentially faster than classical algorithms. Take Shor's algorithm, for instance. This extraordinary algorithm can factor large numbers with ease, a task that would take a classical computer longer than the age of the universe. This ability has profound implications for encryption and cybersecurity. And then there's Grover's algorithm, capable of searching through unsorted databases in record time. It's like finding a needle in a haystack, but at quantum speeds. These quantum algorithms hold immense potential, from cracking encryption to finding a needle in a haystack of data. They are the quantum superheroes, harnessing the strange and wonderful laws of quantum physics to shape our digital future. Secure communication takes a quantum leap forward with quantum key distribution. Now, what makes it special? Let's delve deeper. Quantum key distribution, or QKD, is a method of transmitting cryptographic keys between parties. But unlike traditional methods, QKD leverages the peculiar properties of quantum mechanics to ensure security. Imagine this. Alice wants to send a secret message to Bob. They use QKD, creating a shared secret key. This key is encoded in the state of quantum particles, like photons. If an eavesdropper, let's call her Eve, tries to intercept the key, she'll inevitably disturb the quantum state. This disturbance gets noticed, alerting Alice and Bob to the intrusion. So, you see, QKD provides an ultra-secure method for exchanging keys, making it virtually impossible for anyone to eavesdrop without being caught. With quantum key distribution, we can send secret messages protected by the laws of quantum mechanics. Prepare for a mind-boggling concept: quantum teleportation. This isn't about beaming people or objects from one place to another, like in science fiction. Instead, it's about the teleportation of quantum states from one particle to another. Here's a simplified explanation. In the quantum world, particles like electrons or photons can be entangled, a fascinating process that links them in such a way that the state of one instantaneously affects the state of the other, no matter how far apart they are. Now imagine we have two entangled particles, A and B. Particle A is with us, and B is far away with a friend. We also have a third particle, C, which we want to teleport. To do this, we first make a measurement on particles A and C together. This measurement entangles A and C, and in the process, destroys the original information in C. But don't worry, because the information isn't lost. It's transformed into a set of classical information, which we can send to our friend with particle B. Our friend then uses this classical information to manipulate particle B. And here's where the magic happens. Particle B takes on the quantum state that particle C had originally, effectively teleporting the state of C to B. Now you might be thinking, but isn't this just a roundabout way of transferring information? Well, not exactly. The beauty of quantum teleportation is that the original quantum state is destroyed in the process of teleportation and recreated elsewhere. This could potentially lead to ultra-secure ways of transmitting information, as any attempt to intercept the information would disrupt the quantum state and be detected. Quantum teleportation, while still in its infancy, could revolutionize how information is transferred. It's another exciting testament to how quantum information theory is not only challenging our understanding of the universe, but also paving the way for technological advancements that could transform our world. In the world of cryptography, quantum mechanics promises unbreakable codes. Quantum cryptography, a fascinating intersection of quantum physics and cryptography, offers an entirely new way to approach information security. It utilizes the principles of quantum mechanics to encrypt data and transmit it in a way that cannot be intercepted without alerting the sender and receiver. Imagine a world where your most sensitive information, from personal conversations to financial transactions, is shielded by the laws of physics themselves. That's the potential of quantum cryptography. It doesn't just scramble your messages into indecipherable gibberish. It makes it impossible for anyone to even attempt to read your messages without your knowledge. This is achieved through the quantum key distribution, a method that allows two parties to produce a shared random secret key known only to them, which can then be used to encrypt and decrypt messages. Quantum cryptography, leveraging the peculiarities of quantum mechanics, defends against even the most advanced eavesdroppers. Beyond computing and communication, quantum information theory brings a new perspective to entropy, a concept that might seem abstract, but it's very much real in the quantum world. Quantum entropy, like its classical counterpart, is a measure of uncertainty or randomness. However, it operates on a whole new level. It's the quantum version of the classical Shannon entropy, which quantifies the amount of information in a message. But quantum entropy deals with qubits and the mysterious properties they possess, like superposition and entanglement. Let's take a step back and consider a coin toss. In classical Shannon entropy, there's a 50-50 chance of heads or tails, so the entropy is 1 bit. It's simple, predictable. Now, let's dive back into the quantum realm. A qubit, unlike a classical bit, can be in a superposition of states. It can be heads, tails, or both at the same time. This is where quantum entropy steps in, measuring the information content or uncertainty in these superimposed states. But quantum entropy doesn't stop there. It accounts for entanglement too, where qubits can be mysteriously linked. The entropy of an entangled system is not simply the sum of its parts. It's a complex calculation requiring a deep understanding of quantum mechanics. This complexity is what makes quantum entropy so fascinating and so important. It's a cornerstone of quantum information theory, providing insights into quantum computing, quantum communication, and more. So, while entropy in the classical world is a measure of disorder, in the quantum world, it's a measure of information content in a much more intricate sense. It's a testament to the richness and complexity of the quantum realm. Quantum entropy, another fascinating concept, redefines our understanding of information content. This is the profound impact of quantum information theory, extending beyond our conventional wisdom and challenging us to think in new, exciting ways. Quantum information theory isn't just a fascinating concept, it's driving cutting-edge technologies. Imagine the power and potential of quantum computers. These machines leverage the principles of superposition and entanglement to process vast amounts of data simultaneously, promising computational speeds unfathomable in today's classical computers. But it's not just about speed. Quantum computers can solve complex problems that are currently beyond our reach, opening up new frontiers in areas like drug discovery, climate modeling, and financial optimization. And then there's secure quantum communication. With quantum key distribution, we're looking at an unprecedented level of security, safeguarding our digital world against even the most sophisticated cyber attacks. We're at the dawn of a quantum revolution, where the strange and wonderful rules of quantum mechanics are being harnessed to transform our technological landscape. As we've seen, quantum information theory is not just theory, it's the foundation of a quantum revolution.